slide it, is it still the same size and shape? Yes, so if I can take a triangle and translate it, then those two triangles must be congruent, right? If I take a triangle and I rotate it, is it still congruent? Is it still the same size triangle? Yes. So if you can take a shape and make it land on top of another shape by using a translation, a rotation, or a reflection, then that means those two triangles must be congruent. So it's the first way we're going to learn to prove two triangles are congruent. We're going to try to see, can I make one triangle land on top of another triangle? Okay? But before we do that, we're going to have to review all our transformations and make sure you understand the rules. We only talked about one rule. This was an example of a rule. What kind of transformation did that give me? Say it again. Translation. Remember that if we added something to the x or y or subtracted, that meant we were going to slide it those directions. So this is an example of a rule for a translation. We did not talk about rules for reflections or rotations. We're going to do that today. This means I'm going to translate in what direction and how far? Right 2, down 3. Okay? Remember, x's is left and right, y's are up and down. All right, so you're going to have to draw them and identify and describe them like you just did in the bell word. Then you're going to have to use what's called properties of rigid motion. Rigid motion means you're not stretching it. You're not making it bigger or smaller. It's rigid in that when you move it, you do not change its size or its shape. So we're going to use the properties of that to decide, can we prove two figures congruent? Can I reflect it over here and make it land on top of itself? Can I rotate it? Can I slide it? Can I do maybe two of those? Maybe I have to reflect it and then slide it. But if I can do a series of those transformations, it will land on top of itself, then they must be congruent. Okay? What is the one transformation that we have not mentioned so far? Dilation. Dilations are going to do what to the shape? Make it bigger or make it smaller. We're going to learn two words that we have to use instead of bigger and smaller. Dilations will not prove two triangles congruent. If I make it bigger, it's not the same size, right? So if it takes a dilation to make it land over here, then they were not congruent. Okay? And then we'll talk about these two words. So, dilation. This is the one we didn't talk about in section 1.7. A dilation is going to enlarge or reduce. And so the two words I want you to use are enlargement and number 2, reduction. So just like with translations, I said you have to tell me the direction and the distance. If you tell me it's a dilation, you have to tell me if it's an enlargement or a reduction. Okay, is it getting bigger or smaller? Enlargement's bigger, reduction's smaller. You will be able to determine that by looking at the scale factor. Your scale factor is the letter K, and if K is great, K will always be a number greater than 0, meaning that your scale factor is not going to be what? A negative, and it's not going to be 0. If it's 0, then that means your shape didn't change its size, so it's not a dilation. If it's greater than 0, it could be a fraction, like 1/4, 1/2, 1/3, or it could be greater than 1, like 2, 3, 4, 5. If it's a fraction, like 1/2, 1/3, do you think that it's an enlargement or a reduction? Reduction, because you're making it half the size, a third of the size. So this will be a, oops. Hey, Kaya, since we just had 5 minutes, you're going to wait and then pick up after lunch. And then you can just take the rest of this entire stack after lunch, okay? So you just leave it there till lunch. Okay, reduction is going to be where K is less than 0, but greater, oops, that's not what I meant. K is greater than 0, but less than 1. I'm writing that backwards. What is wrong with me today? K is less than 1, but greater than 0. So K is between 0 and 1. It's a fraction, a half, a third, a fourth, a fifth. If it's an enlargement, K will be greater than 1. 2, 3, 4, 1 and a half. It's going to get bigger. Okay? The rule that you will see will be X, Y will map onto kx, ky. So what are we doing to the x's and the y's? Multiply. We're going to multiply by the scale factor. So if the scale factor is a fraction of like a half, then we're making that number smaller. If the scale factor is a fraction like 5 halves, that's 2 1/2, we're making it bigger. Okay? So we have a scale factor k, we're making a dilation, and then the other thing I want to point out is that our center of our dilation, and all of the ones we're looking at right now, are going to be at the origin. If the center is not at the origin, you can find it by simply taking your image point. So if this were A prime and this were A, connect your image point back to your pre-image, and wherever they intersect, so let's say I had another point here, B prime and B. If I connect those points and draw them back, wherever those lines intersect will tell me where my center is. And I'll show you that in an example in a minute. But your center is always at the origin unless when you go image to pre-image, where they intersect is not the origin. And wherever that is, that's your center. Okay, we already know that. Let's look at an example. So it says apply the transformation. I did not give you the graphs this time because I want you to have it all on graph paper to look back at. So take a minute, graph, it says identify and describe the transformation. So go ahead and graph these 3 points, P, Q, and R. And you should end up with the blue triangle that's up on the board. Okay? When I look at the rule, what does this rule right here tell me? Just by looking at it, I should know what kind of transformation this is. The translation, what direction? Left 4, up 1. If I didn't know that, worst case scenario, I could plug the 1 in for x, the 3 in for y, and I could find the new coordinate, right? And that would give me p prime. But I know just by looking at this rule, and after today, you need to be able to tell by looking at the rule. I will give you problems where you won't be able to graph it. There will be no initial points. It'll just be a rule, and it'll say, what is this transformation? So by the end of the lesson today, you need to know. This is a translation without graphing. So the rule that we learned back in section 1.7 was that if you are adding or subtracting to the x and the y, that's always going to be a translation. So if the rule adds or subtracts, it's always a slide. And then it tells you the direction by looking at that. So since it's a -4 to the x, that means we're going to go left 4, because that's where x's get negative. And since it's a +1, that means we're going to go up 1, because that's where y's get positive. Okay? But again, for today, when you're investigating, if you're not sure what it is, you're going to plug the coordinates in, you're going to find your new points. So on your graph, you should be able to take each of these points, go left 4, up 1. Don't forget to label them P prime, Q prime, R prime. On the homework tonight, if it says apply the transformation, that means you have to graph. I am going to give you points for the graph if it says apply the transformation. So on the homework, make sure you graph it, even if you can look at it and tell. If it says apply, you have to graph, okay? Then if it says identify and describe, this is what we're looking for. Is everybody good with translations? Okay. I'll leave that there. When we get back from lunch, we're going to do the next few slides. I'm going to have you go ahead and graph them when we get back from lunch. So you'll graph each of those pictures, and then we'll talk about what they are, okay? Okay, so now we have these points. We can graph them, so now I'm going to show you what the graph would look like. You can go ahead and plot yours on your paper. So you should have had the blue rectangle before we started. Agreed? Or is there a mistake on this one? Okay, and then now we're going to plot the new one. So you should have a point at 0, 3. That's your R prime. 3, 3 is your E prime. 3, 1 is your C prime, and 0, 1 is your T prime. Does everybody have that? So if you didn't know, you plug the coordinates in, you graph the picture. You look at this picture, and what do you now notice? You went from blue to red. This is not obviously just a reflection across the y-axis. I can't slide it, so it has to be a rotation. What direction? Clockwise. How far? Do you remember when we talked about rotations? If you're not sure how far it is, you can go back to the origin. So pick one point, T, connect it back to the origin. T prime, connect it back to the origin. Whatever angle is made is your angle of rotation. So this is a 90-degree clockwise, thank you. Clockwise, not counterclockwise. Clockwise rotation. Yes, about the origin. And you can either write the word origin or the coordinate 0, 0. Everybody good with that? What do you notice happened when we had a rotation that did not happen when we had a reflection? To the rule. Leah? Okay, so every rotation, the x and y are going to switch. Every time. Okay, now what direction did we go here? Clockwise. So we're rotating to the right. It's the coordinate on the right that's going to change sign. So I'm going to make a little chart over here to help you with rotations and rules. I would write this down because, again, you have to be able to identify what this is without graphing it. So, rotations. We're going to start with clockwise, which is what we just did. 90 degrees. A 90-degree clockwise rotation is going to take the XY and map it onto. It's going to switch them, YX, and it's going to the right, so the one on the right is the one that changes sign. That's kind of how I remember it. If you think about it in terms of an XY coordinate plane, you're going clockwise 90 degrees. So you're going from XY, switching the coordinates YX, and it's the second coordinate that's now going to be negative because you've went from first quadrant to fourth quadrant where everything, where your Y coordinates are negative. So this is now going to be negative. Yes, exactly. And so we'll write that down in just a second. So one more time. If we're doing a 90-degree clockwise rotation, which is what we just did, what we observed is that when you go 90 degrees clockwise, the coordinates always switch. So we have this. That's always going to be true. And if you're trying to decide which one of them changes sign, think about the direction that you're turning it. I'm taking the object and I am rotating it clockwise, which is to the right. So in your ordered pair, it's the one on the right that's going to change sign. Because when you rotate 90 degrees, if I have a point in the first quadrant, it's going to land in the fourth quadrant. And the number that changes, that goes from a positive to a negative from first to fourth, is the Y coordinate, the second number. Okay? So let's repeat that process. Let's do it one more time. So let's say we do a 180-degree rotation. So now XY is going to become what? Very good, Ann. We're going to switch them again. So now I have negative x, positive y, but I'm going to change the sign on the right again, so now it's negative x, negative y. Okay. So the process, if you're doing a 90-degree clockwise rotation, every single time that you do a 90-degree rotation, you switch them, change the sign on the right. So now I'm going to take these, because I've already went 90, I'm going to take these coordinates and do another 90-degree rotation to get a total of 180. So I'm going to take them and switch them and change the sign on the right. So if I switch them, I get negative x, positive y. Now I'm changing the sign on the right again. And okay, we'll get there in a second, but yes, you are right. I'm going to do counterclockwise over here in just a second. So 270. I'm going to do it one more time. So if I take these and switch them and change the sign on the right, what is it going to become? Very good. Negative y, positive x, because when I switch, I get negative y, negative x, and then I change the sign on the right. What would happen if we did it one more time? Same thing as, it would take us right back to where we started. If I switch and change the sign on the right, xy lands on xy, because how far is 360 degrees? All the way back around to where you started, right? Okay, so let's do the counterclockwise. Anne already has said those things that we're going to need to see here. Counterclockwise. So now we're going 90 degrees, but we're going to the left. Every rotation switches the x and y. So we're going to switch the x and the y, but this time if we're going counterclockwise, instead of going from first quadrant to fourth quadrant, we're going from first quadrant to the second quadrant. In an ordered pair, is it the first number that's negative or the second number that's negative in the second quadrant? The first. So when we switch, we get yx, but it's the first number this time that's going to be negative. Again, the way I remember it is, when I rotate to the left, it's the one on the left that changes sign. If I rotate to the right, it's the one on the right that changes sign. Switch the coordinates first, though. So the one on the left is now changing sign. So this is negative y, comma x. Does that make sense? If we want to go 180 degrees, x, y is going to map on 2. So now we need to take these coordinates and do it again, because we're going to do 90 twice, right? So if I take these and I switch them again and change the sign on the left, what's it going to become? Very good, and that's what Anne said. She said, won't it be the same? Think about that. If you rotate 180 to the right, or clockwise, you rotate 180 to the left, or counterclockwise, would you land at the same place? If you take a triangle and turn it 180 this way, or 180 the other way, you're still going to have the same exact thing. So a 180 degree rotation, the direction doesn't matter. So on the homework or on a test, if you tell me it's 180 degree rotation about the origin, you don't have to tell me the direction, because it doesn't matter. It can be clockwise or counterclockwise. Okay. This one? Yeah, that's what we're talking about right now, that those are exactly the same. 180, either direction is exactly the same. Does that make sense? Okay. Oh, you bet. So now if I flip it again, so I'm going to switch again. We're going to do another 90 degree rotation counterclockwise. XY is going to map on 2. So, okay, switch it. So now we're going to have negative y, negative x, but we're changing the sign on the left. So it's positive y, negative x. And then if we do it one more time, very good. 360 degrees, when we switch it, we have negative x, positive y, but we change the sign on the left, so we're back to positive x, positive y. And Evan and Jael, if you're watching this video at home, you cannot see the board. I apologize for that. Hopefully you can hear what I'm saying. It's also in your textbook. Okay, so 270, we're doing 3 90-degree rotations. So first, we switch, change the sign on the left. Then we take those coordinates, switch them. So now this is x and this is negative y, and change the sign on the left. Then we take those coordinates and do it a third time to get to 270. So we switch, we have negative y, negative x, and we change the sign on the left. Does that make sense? Yeah. Why it's negative? Because when you rotate a 90-degree rotation, you are changing quadrants. On a coordinate plane, this is positive, this is positive, this is negative, this is negative. So when I move from first quadrant to second quadrant, all of the x's are negative, all of the y's are positive. So if I do a 90-degree counterclockwise rotation, my x's and y's will switch. That's just the definition of a rotation, what happens. And then because I've landed in the second quadrant, now it's the first number in an ordered pair that represents your x value. That number is now going to be negative. If I go to the other direction clockwise, I'm going from first quadrant to fourth quadrant where the x's are positive and the y's are negative. So when I switch the ordered pair, it's the second number in the ordered pair that represents the y value. It's going to be negative. Okay. No, because I'm switching them first. So this negative x is going here, this negative y is going here, and then I'm just changing the sign on the left because I'm going to the left. Does that make sense? Okay. When you're going clockwise, that's to the right, so you change the number on the right. When you're going counterclockwise, that's to the left, so you change the number on the left. After you switch. Always after you switch. Does that make sense? Okay. So you're going to look at those rules, and you should be able to tell just by looking at the rule. If I look right here, I see, oh, it's been switched, and the one on the left changed sign. So that means I have a rotation. And what do you notice about this 270-degree clockwise rotation compared to over here? What is a 270 clockwise rotation the same as? A counterclockwise 90. And what is a 90 clockwise rotation the same as? 270 counterclockwise rotation. Does that make sense? So if I see this rule, I can automatically think, okay, I switched them and it went to the right because the sign on the right changed sign. So that was clockwise. If I see this one, I can say, oh, they switched them and the sign on the right changed sign. So they must have been a clockwise rotation, 90 degrees. If I want to write it as a 270 counterclockwise, I can. But it's the same as a 90 clockwise. Okay? And 180, the direction doesn't matter. 90 and 270s are always the same, and a 360-degree rotation is not really a rotation because you're back to where you started. Okay? All right, so last one. You graphed it, you looked at the rule, and we just talked about this at the beginning of class. What is this going to tell me that we're doing? Dilation. And it's going to be a what? Enlargement, because remember, this number that we're multiplying by, if it's greater than 1, is an enlargement. It's making it bigger. So when you look at the picture, what you're going to do to find those coordinates is just simply plug these numbers in and multiply them by 3. Yes, because the rule in our notes that we wrote down to start with was xy maps onto kx, ky. So the k in this case is 3. Okay? So that means that this is, just by looking at the rule, a dilation. And by the way, biggest misspelled word. It's dilation. It is not dial. It is not D-I-A. It is dilation. There is no A here. Dilation, enlargement, and when you tell me it's a dilation and that it's an enlargement, you need to also tell me by how much. So it's a dilation, enlargement by a factor of 3. You are multiplying by 3. You would be dividing, or still they would look at it as a multiplication. It's just you're multiplying by a fraction less than 1. So you're dividing by 3 or multiplying by a third. Okay? So to get these coordinates, what did we do to all of these coordinates? We just multiplied them by 3. Now, that only works if the center is at the origin. I'm going to say that again. Multiplying by 3 only works if the center is the origin. And that also means a rule for a dilation only works if it's centered at the origin. You cannot write a dilation as a rule like this if the center is somewhere else. Okay? So if the center is not at the origin, you cannot simply just multiply by the number, by the scale factor. How do I know it's the origin? Everybody look up here real quick and make sure you're with me. If I want to find the center of my dilation and it's not at the origin, the way to find it again is to pick a coordinate, that's a prime, connect it to its pre-image, so k prime to k, draw that line. Then pick another coordinate, L prime, connect it to its pre-image L, and then look to see where do they cross. These two crossed at the origin, so I know this is my center. So if your center's not at the origin, when you draw the lines, it'll cross somewhere other than 0, 0. Okay, so prime to pre-image, draw the lines, see where they cross. It gives you your center every single time. Because what's happening is you're enlarging it from that point, or you're reducing it down to that point. Everybody with me? Okay. Questions? Okay, so here's the big chart. Again, Evan and Jael and Kaya, when she looks at this, here's the big chart of everything I wrote on the board. This is all about clockwise, and then this is about counterclockwise. And we did say that this 90 is the same as a 270 counterclockwise, and this counterclockwise 90 is the same as a 270 clockwise. 180 doesn't matter the direction, and you need to be able to look at these rules and be able to tell me automatically what kind of information or what kind of transformation this is. Okay? Any questions? You have it in your notes. You have the whole chart in your notes. Okay? All right, so a couple words we need to talk about is isometry and rigid transformation. An isometry is a transformation that preserves length, angle measure, and area. 3 of the 4 transformations we just talked about are isometries. Which ones that we talked about preserve length, angle measure, and area? Very good. So reflections, rotations, and translations are all isometries. They are all isometries, every one of them. Which means what's the only one that does not preserve area? Dilation, because it gets bigger or smaller. A rigid transformation is just another name for isometry. So on the vocab test, it'll say another name for an isometry. Don't pick isometry. Pick rigid transformation. They mean the same thing. If it's rigid, it does not change the size or the shape, which means it's an isometry. So they're going to, I don't care either way. Translations, reflections, and rotations always give you something congruent to their pre-image. Dilations that have a scale factor not equal to 1 produce images that are not congruent to their pre-images. If it's equal to 1, if I take every coordinate and multiply it by 1, is it going to change its value? No. So if your k value is 1, it wouldn't increase it or decrease it. So therefore, dilations have to have scale factors greater than 1 or less than 1. Okay, so here is what they're going to do next. They're going to ask you to determine whether the polygons with the given vertices are congruent. For these, you can still on your graph paper graph them if you want to have it for your notes. But I am going to go ahead and just provide you with the picture up here on the board. I don't think I gave you the picture in your notes, though, did I? Okay, so you can either pull them up on the reminder right now, take a few minutes and graph these points. But for the homework, if it says determine whether the polygons are congruent, that means it's not a proof, but you are proving that these two triangles are congruent by listing the transformations that cause them to land on top of each other. So you're going to look at the two transformations. It does not tell you which one is the pre-image, so let's just all go by the first one is the pre-image, okay? It won't be wrong either way, but it'll help us be more consistent when we're comparing answers. So we'll call the first one they list the pre-image, the second one the image. You're trying to figure out how can I take the blue triangle and make it land on the red triangle? Or can I even do it? It says determine if they're congruent. So does the blue look to be the same size as the red? Yes, so then that means we should have a transformation that would make blue land on red. For this part, you're trying to come up with one transformation, okay? So is there a transformation that you see that would make blue land on red? Translation, okay? So then you're going to be very specific. You're going to say translation. How far? What direction? Down 3. I'm going from positive 3 to, positive 1 to, that should be a negative 2. That is a typo. Fix that. Is it? So I'm going from positive 1 to negative 2. Everybody agree that's down 3? And I'm going from negative 3 to negative 4. So I'm going down 3 and left 1. So this is a translation. Down 3, left 1. That's great. I want you to be also be able to write it as a rule. So what would that be as a rule? X, Y, arrow. Very good. X, oh, hold on, say it again, Aaliyah. Careful, down is going 3. So down is going to be my Y values, up and down. And it might be better if I write it in that order so it doesn't confuse you. Left 1, down 3. So it's going to be what, Aaliyah? Very good. So be able to write me a rule, also be able to describe it. For tonight's homework, I want you to do both because you're trying to practice for the test, okay? On the test, I'll try to make sure I'm clear whether I just want you to identify and describe or whether I want you to write a rule, okay? But for tonight's homework, if it says determine if they are congruent, if you say yes, they're congruent, do both. Tell me the information, identify and describe, and write the rule. I'm totally fine if you abbreviate like that, yes. Is that your question, Harry? Okay. Totally fine with me. You can write it out if you want to, too, though. Okay, look at the next one. Blue to red. Identify or determine if these are congruent. Do they look to be congruent? No. So you could just say no, unless it says explain why or why not. If it says explain why or why not, you need to tell me what it is. So first of all, if I look at this, I need to see if I think I know what it is. So if it's not translations, reflections, rotations, what does it have to be? Dilation. Let's see if the center is at the origin first to see if we can write a rule. So I'm going to connect my points back, connect my points back. Are they all crossing at the origin? Yes. So this does have its center at the origin. It is a dilation. How can I tell how much bigger it has gotten? What it's multiplied by. So what did 2 become? 3. What did negative 2 become? Okay, that's a little harder to see what to multiply by. So here's the rule that I want you to write down in your notes. K is always equal to the image divided by the pre-image. Image divided by pre-image. It doesn't matter where the center is. Whatever the image length is divided by the pre-image length is always your scale factor. Now, if the center is at the origin, you can just use the coordinates. If the center is not at the origin, you need to use the length of the side. So I'm going to work it that way just to show you what I mean. So instead of looking at the coordinates, what's the length of this little side of the triangle? 2. What's the length over here of this side of the triangle? 3. So now what's the image and what's the pre-image? We're going to go with the second one is the image. So that was the one here. So the image is 3 and the pre-image is what? 2. So my scale factor is what? 3 halves. So if I took each of these coordinates and multiplied them by 3 halves, I would get these new coordinates I have here. So I would write down no, this is a dilation. What kind of dilation is 3 halves? Enlargement, because it's bigger than 1, right? So it's a dilation, enlargement by 3 halves. How would that look as a rule? Okay, and be very careful that you always start with x, comma, y, arrow, and then 3 halves x, 3 halves y. Okay? Because you're telling me to take the original points and map them onto this new point. So you're giving me the entire transformation. Okay. This is just going to be another example like that where they want you to determine if the polygons with the given vertices are congruent. Then they want you to support your answer by describing the transformations. So again, it's the same exact kind of idea. I'm going to look here at Rachel's paper to see how many we have left here. Okay, so I'm going to skip that one since it's the same thing. And I want you to move over to the next one. Now it says prove that the polygons with the given vertices are congruent. prove is basically the same thing as what we've been doing. So I just want to make sure you understand that with the directions, it's nothing different. If it says prove, we're not writing a two-column proof today. We're just listing the transformations that would make one triangle land on top of the other triangle. Okay? When they say prove, though, you may have to use multiple transformations on the homework tonight. It may not be just one reflection. It may be a reflection and a translation. So you may have to reflect it and then slide it. Or you may have to rotate it and then reflect it. They get a little more complicated. Look at this one, though. Are these two congruent? Okay. In this case, it may be because my scale here is not exactly the same. So I want you guys to take a minute and graph these two and make sure they really don't look like they're congruent. So that scale up there is not consistent on the board. The x-axis is skinnier in between than the y-axis is. So you don't have to use the graph, just use those coordinates. A, B, and C. Graph those. And they're on your notes right there beside you too if you can't read the board. And then P, Q, and R. Okay, so they do look to be congruent on your paper. Do they look like they're congruent to everybody? Okay, so Anne thinks it's a rotation. Does anybody else think it's a rotation when they look at their paper? Okay, now here's where you have to be careful. If it's a rotation, first of all, which one of these is the pre-image? Okay, the blue. We said we're going to make the first one the pre-image, right? So this one is the pre-image. So what direction are we rotating? Counterclockwise. How far? Okay, we think it's 90 degrees counterclockwise, and you think it's about the origin, right? Okay, so if I rotate, and again, we're going to stick with about the origin for now. So rotate 90 degrees counterclockwise about 0, 0. According to what we just talked about, that means if I go 90 degrees counterclockwise, what's counterclockwise, left or right? Left. Then that means I should be able to take these coordinates, x, y, and they should do what if I switch and go to the left? Okay, I feel like Anne has got transformations down, and I want to make sure everybody else is not like falling behind. So we said to do a rotation, I switch, and I change the sign on the left because I'm going to the left, right? Okay, now I want you to check. If I take A and switch them and change the sign on the left, do I get P? I don't, do I? So it is a rotation, 90 degrees counterclockwise, but it's not the only transformation. It didn't make it land on top of it by itself. So we're going to have to do that transformation and then look to see, is there another transformation I need to perform to get it to land on top of itself? So that's where I said some of these proving ones are going to have multiple steps. So look at the picture and first decide, do I need to rotate it? It definitely needs to rotate. Now let's do the rotation. So take point A, switch it, and change the sign. What is A prime going to be? Okay, Rachel said -2, 1. Let's go ahead and do B prime, -1, 2, and C prime. Okay, now I'm hearing more people. I like that. Everybody with them. Eduardo, Carlos, you guys are quiet. Aaron, you with them? You sure? Okay, so switching, changing the sign on the left. Plot those points. So -2, 1, -1, 2, and -2, 4. And plot it on your paper so you can look at it too. Now do you see a second transformation that would take the green triangle and make it land on the red triangle? Good, Claudia. Translation, go ahead and tell me how far and what directions. So we're going to translation. Tell me one more time, left how far? Left 1, down 3. Yes, it would. Very good. So on the homework, one more time, I want you to do both for tonight because I want you to practice both for the test. So for the first transformation, we would have x, y, maps onto what I wrote up here, negative y, x. And then for the second transformation, we would have x, y, maps onto, and then it would be x minus 1. And actually, I'm going to change that. Don't do it like that. Just kidding. Keep your arrow going. Because you're not taking the original points, you're taking the points in the middle and doing it, right? So first you're going to take them and rotate them. Then you're going to take those points and you're going to translate them. So it'll be x minus 1, y minus 3. Yes, and the order in which you do them, you need to list them. So one more time, we're taking the original points and rotating, and taking those points and translating. And if we can do a reflection, rotation, or translation, then they must be congruent. And this is what you're writing down as your proof. It is a list of transformations that made them land on top of each other. Questions? Are you confused about why I did 2 arrows here? Because when we did this, we took these coordinates and we rotated them to get these new coordinates. We're not going back to the blue figure and sliding it. We're taking the green figure and sliding it, so we want to use these coordinates to translate. Does that make sense? Okay. All right. And then you should just have one more problem that says prove, right? Do we need to do one more example here, or are you getting the idea? I'm happy to do it if you want to. Yes? Please work that one. Okay, let's go ahead and do it. We've got a couple who want to. So on your paper, go ahead and graph these 2 figures on your graph paper. Let's see, I've got 17 minutes. Yes, exactly. Is that making sense? Okay. Is your picture turning out to be congruent? It's got a mistake, doesn't it? Darn it. Yeah, no, if it says prove, then that means they are definitely congruent. So I knew one of these had a mistake. I couldn't remember which one it was, and I didn't get it changed because of that. Sorry, guys. Let's do one off your homework. How about that? Okay, put a clean sheet of graph paper so you can do one off your homework. Okay, let's do number 10. Number 10. So write number 10 down on your paper. And then we're on page 220 in your textbooks if you want to open that up. And if you're watching the video from home, I'm just going to change this problem to number 10, which says prove. And it has page 220. If you don't want to mess with opening your book, I'm going to write the coordinates up here on the board. So here's D, E, and F we're going to graph. And then the other shape is going to be X, 3, 4, Y, 6, 3, and Z is 3, 1. So let's graph these on our graph paper. And then we're going to prove that they are congruent. If it says prove, they should be congruent. If it says determine if they're congruent, you can have answers that say no. Do yours look like they are congruent when you graph them? Okay. So now you're trying to get the green to land on the red up here in the picture. Or excuse me, the red to land on the green, because we're going to do first one is your pre-image, second one is your image. So does it look like, look at your picture, because mine's not near as good up here with my graph just kind of hand sketched. Do you see a transformation that you know for sure has to occur? A rotation, a reflection. Okay, so maybe you try a reflection and see if you can figure out a way to get it on it. Maybe you try rotation to see. So figure out what you think it is. If you think it's a reflection, let's start there. What do you think you're going to reflect over? Y-axis? Okay, let's try it. Okay, you think it's over x equals 1? Okay, so let's try that. So x equals 1 would be this line. So if I reflect it across that line, it's going to go 1, 2, 1, 2. 1, 2, right? Because F and, 1, 2. And then E is 5 away, so it's going to go 5 on the other side. It's actually down just a bit. So this is E prime, F prime, D prime. Is it to where it can just slide up and land? No, mine's hard to see, but if you look at yours on your paper, this one is closer to the X, this one's closer to the D, right? So how else can I get this one to land over here? If I do another reflection, will that work? What would I need to reflect across to get it to land there? Okay, so maybe negative 0.5. It's really not meant to be that hard, so if you're having trouble and can't figure it out, let's go back and try. And you may be able to find a line of reflection where it works, so feel free to keep going with the reflection idea. But I'm going to go back to, I heard rotation before that, right? So let's try rotation. What direction do you think we need to rotate? Doesn't matter because you think we need to go how far? 180. So let's try that, 180 degrees. What happens to the coordinates if we go 180? Okay, negative x, negative y. So all of these coordinates should change signs, right? So d prime should be at positive 1, positive 5. E prime should be at positive 4, positive 4. F prime should be at positive 1, positive 2. Do you all agree with what I'm doing there? 180-degree rotation does not switch them because you've actually switched them twice, and the signs change on both of them. So all I did was take every one of these coordinates and change their signs from negatives to positives. Okay? Because that's my rule if I'm doing 180-degree rotation. Now let's graph that shape and see. So I'm going to graph 1, 5, 4, 4, and 1, 2. You graph it on your paper because you'll be able to see it better than mine up here on the board. Once you have it graphed, do you see a second transformation that would make the black one land onto the green one on your paper? And the translation would work this time, right? How far would I need to translate? Okay? Right 2, down 1. So remember, you're going to keep your rule going. So I'm going to rewrite this where I have more room, okay? So I would say xy maps onto negative x, negative y, and then we take those coordinates and map them onto, okay, x plus 2 because we're going right 2, and then y minus 1 because we're going down 1. You would write it out as a rule, and then I want you to list it so we'll know. So this is number 1. We did a rotation 180 degrees about the origin. And remember, 180 degrees does not matter direction, so you don't have to tell me. Or you can pick one, but the direction doesn't matter. And then the second one was a translation. And it was right 2, down 1. Say it again. Yeah, you can list this and then write your rule. Sure. Leah. Yes, you can definitely abbreviate R and D, L and U. All of this and all of this. And again, on the test, I'll specify if I want a rule or an identify and describe. But for now, since we're practicing, I want you to do both. Okay? Might have been able to make the double reflection work, but if you can't and it's getting hard, go back. Can you see another way to make it work? The homework problems are not meant to be super hard. So maybe the route you're going isn't working. Okay? Questions? We didn't get to 4-2 and it's okay. We will not get through all of 4-2 and 4-3 tomorrow. That's okay. We only have one section on Monday, so whatever we don't get done tomorrow, we'll just finish up on Monday, okay? If you have one page, you will definitely need graph paper for the assignment. And also remember, if it says apply, what do you have to do? Okay, what does that mean? Graph. If it says apply, you have to graph. You're graphing the pre-image and the image. Sorry, me too. Look back at your notes. See what we did in the notes if you're not sure what you're supposed to show. The ones I'm going to send out probably won't have everything I wrote down in the video. So watch the video again if you need to.